Hello, my name is Aaron Dodson, and today I'd like to introduce you to Emscripten. Now, the first thing you might be wondering about Emscripten is, what is it? Put simply, Emscripten is a compiler. However, unlike most compilers, which take C or C++ input source files and convert them into executable machine code instructions, Emscripten takes a different approach. For its input, it takes LLVM bitcode, that is, virtual machine instructions generated by the Clang compiler for the low-level virtual machine, and transforms them into JavaScript. The resulting JavaScript is able to be executed on web browsers as well as JavaScript engines such as Node.js and SpiderMonkey, allowing it to be run on the web and on local systems through a JavaScript engine. At first, Emscripten may seem like a solution in search of a problem. However, a brief amount of thought will show that there are many reasons why it is a useful tool. First among these is legacy code bases. Today, there are millions of lines of C and C++ code already in existence and in production. This code is tested, performant, and very useful for the job it performs. But, as the world is changing, more and more software is moving onto the web, and onto JavaScript. Rather than having to rewrite and re-debug this code, Emscripten allows it to be ported with very little effort, especially compared to what would be taken to do a full line-by-line port from one language into JavaScript. Additionally, Emscripten allows greater programmer productivity. While many programmers today are more comfortable in dynamically typed languages such as JavaScript, others are much more productive and comfortable in traditional languages like C and C++. Emscripten allows these developers to continue to do their best work and target it at modern platforms and systems. Indeed, that's yet another benefit. Since JavaScript is cross-platform, so too are programs compiled using Emscripten, even if they originally targeted a specific machine architecture. In general, Emscripten simply allows greater flexibility. It allows code that has already been around and proven to be run on new systems and new environments with a minimum of difficulty. And it's still reasonably good performance, even relative to the original C and C++. Emscripten is sort of different from most compilers, in that whereas most compilers attempt to go from a high-level language to a low-level language, Emscripten has the opposite job. As such, although its structure takes guidance from traditional compiler design, it is somewhat different. Emscripten itself is written in JavaScript, and the main entry point is a file named compiler.js. It invokes three other primary subsystems in its work. First of these is the inner typer. After reading in the LLVM bitcode, it is split into separate lines, and this data is passed to the inner typer for further work. The inner typer's job is to attempt as closely as possible to map the bitcode onto an internal representation within Emscripten, trying to get it close to JavaScript instructions that will ultimately be outputted. Once the inner typer has done this work, it returns the internal representation to the compiler, which then passes it on to the analyzer. The analyzer's job is to perform optimizations. Just like in traditional compilers, Emscripten has a great deal of importance placed on optimizations. Without them, performance would not be nearly what would be expected, and since JavaScript is already slower than the traditional C or C++ that most code being compiled to Emscripten was targeted at, performance is a critical issue. The analyzer's job is to gather as much type information and other metadata as it can to be able to be used for optimizations. Since the more of this data that is known, the better the optimizations can be, it uses several passes and an actor model to try and establish as much information about the source code as possible. After doing these passes, it returns an annotated version of the internal representation to the compiler, and the compiler then sends this internal representation to the JSifier for final output. The JSifier, as the last stage, has the important job of actually outputting JavaScript, given the annotated internal representation. Before it does so, it outputs a preamble and epilogue to provide basic runtime support and boilerplate code for the code generated by it later. After this has been done, the JSifier converts the input code into JavaScript and outputs it. And once this is done, it does one final pass using the relooper, which is a tool that attempts to recreate the native loops in the original source code to improve performance further still. The relooper has an interesting task. Since LLVM bitcode is very simple, there are no loop or if-else constructs, there are simply branches. It loses a lot of the original data that comes along with source code as written by humans. And since most JavaScript engines are optimized for normal code, the sort that programmers write every day, without this information, many of their optimization tricks are not nearly as effective. For example, tracing compilers look for loops and if-else statements when they're searching for hot traces, that is, code that they aim to recompile at a higher level of optimization to improve performance, and these things are also useful for branch predictors. Without these constructs, the code can simply be stepped through one instruction at a time, which prevents many optimizations from being executed. As a result, performance could have a serious impact. Given this, the relooper's job is to attempt to analyze the code and reconstruct these original control flow structures. It takes as input a set of basic blocks, and by analyzing their labels, looks at reachability and tries to reconstruct loops and if-else statements, seeing if one block is accessible from another, and if the branches allow this to occur. So it'll attempt to merge these blocks together and recreate actual for loops or if-else statements in the JavaScript that is output by the JSifier. Whether intentional or not, most C and C++ code is written with certain expectations about the underlying runtime environment. Many of these assumptions don't hold on the web or in JavaScript engines, and as a result, Emscripten needs to take steps to work around these problems. For example, native code expects access to the file system, to a large heap, and to graphics libraries. Many of these are not present in their standard form within the web, so Emscripten provides shims or emulated recreations of them. For example, the heap is implemented as a large JavaScript array, which is then written to by JavaScript implementations of C standard library functions such as malloc and free. Thus, code can use the normal functions that it already calls, but these are dynamically rewritten to use JavaScript and to act upon Emscripten's underlying runtime environment. Additionally, Emscripten implements its own file system emulator, and also links in a copy of the SDL library rewritten in JavaScript to target WebGL and allow graphics output on the web. Emscripten offers several options for programs that need to deal with the file system. For those programs that simply need to read from pre-created data files, this is relatively easy. The contents of these files can be embedded as data within the output JavaScript, and then Emscripten's JavaScript file system API can be used by the program to read and write to these files through the standard C library calls. However, for programs that need more advanced file system access, or for programs that wish to integrate with JavaScript outside of that generated by Emscripten, it may be necessary to dynamically be able to create and delete files. For this, Emscripten provides its own JavaScript file system API that provides methods to allow the creation, deletion, and modification of files, as well as accessing their contents and persisting the entire file system for restoration later. That being said, Emscripten is not without its limitations. One of these is that threads with shared state are not really possible to recreate in the JavaScript environment. Although web workers allow some sense of multithreading to be accomplished in a workaround mechanism, shared state is not possible. Additionally, some operations on numeric values are problematic. Since JavaScript uses 53 bits of precision for numbers, 64-bit integers cannot be directly represented. Emscripten offers several options. It can either preserve the original language's semantics by using an emulation shim for these operations, or it can switch to JavaScript semantics and implement them in much faster native JavaScript operations. Additionally, low-level hardware-dependent instructions are not compatible with Emscripten. Indeed, these instructions are not portable in the original C or C++ code. They would need to be rewritten for each target architecture. Just as in Emscripten, they'll simply need to be retargeted to either be portable or to work within the web environment. Since performance is a powerful motivator for writing code in C and C++, the results of performance under Emscripten could be very relevant to those considering using it to port code. Fortunately, overall these results are quite good. Although at unoptimized levels, Clang outperforms Emscripten by a noticeable margin, at levels 01 and 02, Emscripten is only 2 to 8 times slower, or in some rare cases even faster than Clang code compiled through Clang. These benchmarks show the result of a program using several loops, which is a large part of why performance is notably less at the no optimization level. At the higher optimization levels, Emscripten uses the relooper to recreate the loops, if statements, and other control flow statements. These in turn are able to be run much more quickly by JavaScript engines, resulting in much better overall performance. Depending on the input program and its nature, performance will obviously vary, but in general, Emscripten should impose no more than an order of magnitude worth of Emscripten will impose no more than 1 order of magnitude's worth of overhead. At this point, I'd like to give you a brief demo of some of the things that Emscripten can do. We'll begin with a demo of PNG Crush ported using Emscripten. PNG Crush is a popular utility used to reduce the size of PNG image files by running different compression algorithms and filters on them. This demo also shows how to interact with code generated by Emscripten from other code in the page, and how to deal with the file system API to an extent. To begin with, you'll notice that we're using the new HTML5 file upload API. When we get a file, we read it in using a file reader, and when this is done, we access the data from the file. We then switch over to using the Emscripten JavaScript API to create an input file containing the data that we read from the file off the user's drive. Additionally, an output file is created with no contents to be written to by PNG Crush. Next, we will call the main function, which was compiled by Emscripten into JavaScript. Since main requires an array to be taken as input, this is somewhat more complicated than most function calls would be, which could be done using the ccall wrapper, which requires specifying simply the return type, the argument type, and the arguments themselves. In this case, we need to construct an actual data array based on the arguments that we're giving to the program, including the input file and the output file, as well as some padding to have it properly aligned. Once constructed, this file is passed to the main function through a call to the module API. Moreover, once the program finishes executing, we will use the download file button to access the data in the file that was written out by Emscripten. Earlier, when we created the output file, we stored a reference to it into this variable, which we access here to read its contents and save them into a data URL. Let's take a look at how it actually works. By default, we have a fairly basic window. We've added a browser button here, so let's choose a PNG image off of the desktop. As soon as we upload it, Emscripten, or more specifically PNG Crush compiled using Emscripten, will convert it into a compressed representation. This takes a while since it's running in JavaScript, but after a while, we see the results. PNG Crush took the original image and after running several compression algorithms on it, managed to reduce the file size by about 52%. We'll prepare this file for download, and in due course, we can click the download link to download it. Due to an implementation detail, the file we're getting is actually an array of 8-bit integers, so we'll need to use a small conversion script to convert it into the final PNG image. Let's just change over to the desktop, invoke the script, and see what happens. As you may have noticed, there's now a process.png file. The original, screenshot 2, is here. Note that screenshot 2 comes in at 203 kilobytes, whereas the processed file comes in at only 97. This shows the compression that PNG Crush was able to achieve while running in the browser. Also able to port much more complex programs. For example, this is a Tetris clone implemented using the Qt library, running in the browser. As you can see, we have examples of graphics and keyboard interaction. In short, we're actually playing the Tetris game in the browser, written in JavaScript, whereas the original was written in C and C++, targeting the Qt framework. Performance is quite good, especially for a fairly simple program like this, but Emscripten is able to convert even heavyweight programs, although performance will suffer to some extent.